In this video, we're going to define and discuss the inverse trigonometric functions. Now remember, an inverse function is only defined for one-to-one functions. Those are functions that pass the horizontal line test. And we just went over all of our graphs of trig functions, and they don't pass the horizontal line test. But we can find an inverse trig function as long as we restrict the domain of the original trig function. So we're going to take our trig functions and just look at a small section of them and define an inverse on that section. We're going to start with the definition of the inverse sine function. So the inverse sine or arcsine is denoted by sine with a little -1 of x, that's sine inverse of x, or arcsine of x. And this is the inverse of the restricted sine function y equals sine of x for x just in between -pi/2 and pi/2. So what would this do when we take an inverse sine of something? Instead of calculating sine of an angle, it's going to give us the angle that results in a certain sine. So in other words, let me write the definition we're going to be using. So in other words, y is equal to the inverse sine of x if and only if sine of y is equal to x, where x is between -1 and 1, and our outputs are in between -pi/2 and pi/2. So the input values are between -1 and 1 because our sine function goes between -1 and 1. So the range of sine becomes the domain of inverse sine. And the domain of our restricted sine is now the range of our inverse sine. So let's evaluate a couple things with this inverse sine function. So let's just evaluate. We'll start with sine inverse of the square root of 2/2. And what you have to think to yourself is what angle results in sine of that angle equals square root of 2/2. And using our unit circle, we know that that should be an angle of pi/4 if we're using radians. Now this pi/4 is in between -pi/2 and pi/2, which is the range of our inverse sine, so that is the answer we are looking for. The next one, let's do arcsine of -1. Now remember, arcsine is just another notation for inverse sine. It's the exact same function. So this is saying what angle, when I plug it into sine, will give me an answer of -1. Using my unit circle, you might think that the answer would be 3pi/2. However, we're only using values between -pi/2 and pi/2. So the answer is -pi/2 because that's the same thing as 3pi/2. Remember, 3pi/2 is the angle that goes around this way. -pi/2 is going the other direction, but they are coterminal angles. Last one, if I try to calculate the inverse sine of -3, you're not going to find an answer because sine of any angle is something between -1 and 1. I'm never going to get -3. So this is undefined because -3 is not in the domain of our inverse sine. So that's our definition of the inverse sine. Now let's define the inverse cosine and the inverse tangent as well. So we're going to make a chart. We're going to have a chart that shows our restricted function, the inverse function, and just a sketch of the graph. And we already talked about inverse sine, but I'm going to write it down again. So my restricted function is sine of x, and I'm restricting my x values to be between negative pi over 2 and pi over 2. And I know my output is between negative 1 and 1. The inverse function would then be y equals inverse sine of x, or arc sine of x if you prefer that notation. And it's defined by y equals inverse sine of x if and only if sine of y equals x. And our domain and range flip. So my x has to be between negative 1 and 1, and my y is between negative pi over 2 and positive pi over 2. What does this graph look like? Well, if this is 1, negative 1, I have pi over 2, negative pi over 2. I'm going to have a point down here at negative 1, negative pi over 2, and a point at 1, positive pi over 2, and it just kind of curves like that. That's approximately what the inverse sine graph looks like. And now let's define our inverse cosine. So to define the inverse cosine, we first have to restrict the domain of our cosine. So y equals cosine of x is going to be our restricted function, and we're going to restrict it between 0 and pi. Now, know that there's more than one way to restrict the domain on our functions, and there's really no standard way to do it. This is just the way we're choosing to do it for these particular videos in this particular class. But there are other definitions out there that are perfectly valid. But this is the restriction of the domain that we're using, x between 0 and pi. And our outputs, of course, are between negative 1 and 1. My inverse function is y equals cosine inverse, or arc cosine if you prefer the arc notation. And this is true if and only if cosine of y is equal to x. And our domain and range flip. We're restricting x to be between negative 1 and 1, and the output y is going to be between 0 and pi. The sketch of this graph, we have a point up here at negative 1 pi, we have a point at 1, 0, and it just kind of curves on down like that. That's an approximate graph of the inverse cosine graph. Now let's define the inverse tangent. So the inverse tangent, we need to first define our restricted tangent function. And we're going to restrict our tangent so that its inputs are between the two vertical asymptotes, negative pi over 2 and pi over 2. Your y value is any real number. So this notation here is saying y belongs to the real numbers. We have vertical asymptotes at x equals plus or minus pi over 2. Then my inverse tangent, tan inverse of x, or arctan of x, is defined as y equals tangent inverse of x if and only if the tangent of y equals x. My x value, my input, is any real number, and I have my output is between negative pi over 2 and pi over 2. So the domain and range flip again. Instead of having vertical asymptotes, I'm going to have horizontal asymptotes at y equals plus or minus pi over 2. So if this is pi over 2, and this is negative pi over 2, your inverse tangent function has horizontal asymptotes there, and it looks something like that. All right, so let's evaluate some things using these inverse trig functions. So we'll start by evaluating inverse cosine of negative 1. So we have to think about what this means. This is saying what angle, when I plug it into cosine, will give me a result of negative 1. And that, of course, is going to be pi. And that output is in my range of acceptable values. Now let's try an inverse tangent of the negative square root of 3 over 3. Now this one might be a little bit harder because we're not as familiar with tangent values as we are with sine and cosine. But I do know, if I simplify this a little bit, square root of 3 divided by 3, well, that's the same thing as a negative 1 over square root 3. And that negative 1 over square root of 3, that's the same thing as a 1/2 on top, square root of 3 over 2 on the bottom, and it's negative. Now, why in the world would I write it like that? Well, because I know 1/2 and square root of 3 over 2 are some of the values on my unit circle. I know tangent is sine over cosine. So I want a value that makes the sine 1/2 and the cosine square root of 3 over 2, and one of them has to be negative. And we want a pi over 6. And if I make it a negative pi over 6, that will get me the negative result there because my sine will be a negative value. One last one. What is arctangent of 0? Well, that means that I want an angle that when I plug it into tangent, I get 0. And tangent will be 0 when sine is 0 and cosine is not 0. And that happens at an angle of 0. Now, what happens if we're not directly on the unit circle, though, one of our special values? Well, then we can use a calculator to approximate things. So let's use a calculator. To approximate the degree to 1 decimal place, or radian to 4 decimal places, measure of theta, subject to the conditions. And so for my first one, we want to find the measure of theta. I have sine of theta equals negative 3 over 7. And I want my theta to be between 180 degrees and 270 degrees. So in order to find theta, I'll have to do an inverse sine of both sides of this equation. So I know theta is going to be the inverse sine of -3/7. Now, notice that the restrictions given to me on theta are in degrees, so you're going to want your calculator in degree mode. If you type this into your calculator in degree mode, it's going to give you something like -25.4 degrees. But the problem is -25.4 degrees does not fall into this range here, 180 degrees to 270 degrees. So that's not the right answer, but we can figure out the correct answer by taking a look at what these angles look like. -25.4 degrees is somewhere over here. This is not perfectly to scale. We'll just say that's -25.4 degrees. Now sine, we know on our unit circle, sine corresponds to the y value of the points. And where do I have the exact same y value? Over here at this angle. And what is that angle that goes all the way around to here? Well, that would be 180 degrees plus 25.4 degrees. So I'll say theta is 180 degrees plus 25.4 degrees. And that means that my answer is theta is 205.4 degrees. And that's all there is to it. So you can use the calculator to get a start, but then to make sure it fits in the proper range, you have to take a look on what the graph would look like and kind of figure out which angle they actually want you to find. Let's do another one of these. So part B. Tangent of theta is -8/3, and we're going to have theta between pi/2 and pi. Well, if I start, I can find theta by doing tangent inverse of -8/3. That's going to be theta. If I type that into a calculator, I get theta is -1.2120. Now make sure you have your calculator in radian mode before you type it in, or you're going to get something completely different. So make sure it's in radian mode because our theta was in radians this time. And you'll get theta is -1.2120. But this is not in the desired range of values that we have. For reference, this pi/2 is about 1.5708, and pi is 3.1416. And this does not fall in that range. It's a negative value for one thing. So let's take a look. -1.2120 radians is somewhere over here. And we know that the tangent is sine over cosine. And down in this quadrant here, my sine is going to be, since it's my y value, it's going to be negative, and my cosine is going to be positive. So I'm going to get a negative over positive, which is negative, matching what I have here, a negative value inside of my tangent inverse. But that's not in the proper range, and the proper range is this third quadrant up here. So I want something in the third quadrant because that's between pi/2 and pi. And just double checking, would I have a negative value for tangent up here as well? And I would. This time my cosine would be negative and my sine would be positive, but tangent would still end up being negative. So I want whatever this value is here. Well, there's a couple ways to get that. I can either figure out how much is in between here and do pi/2 plus that, but it's easier to note that this angle here is 1.2120 radians because these angles are directly opposite of each other. And so the angle that I'm looking for, theta, is pi minus 1.2120, which is about 1.9296 radians. And again, that's all there is to it. You type it in your calculator and you just adjust appropriately if it's not in the proper range. All right, so now let's talk about what happens when we compose a trig function with its inverse trig function. Well, as you might expect, sine of sine inverse of x is going to be x because we have an inverse function relationship. But of course, this is only true for values that are in the domain of our functions. So I have for -1 less than or equal to x less than or equal to 1, I will have sine of sine inverse of x equals x. Similarly, sine inverse of sine of x is also equal to x, but that's going to be for x values between -pi/2 and pi/2. This works with all of our inverse trig function relationships. So I have cosine inverse x is x if x is between -1 and 1, and cosine inverse of cosine of x is x if x is between 0 and pi. So again, this is just based on the restricted domain for our restricted trig functions and the domains of our inverse trig functions. Tangent of tangent inverse of x is x, and that's for any value of x because we have a domain of any real number for tangent inverse. And tangent inverse of tangent of x is x as long as we're on that restricted domain for tangent, -pi/2 to pi/2. All right, let's do a couple examples evaluating compositions of trig functions and their inverse. So an example, our first one, let's do cosine of cosine inverse of -1. Well, cosine of cosine inverse of x is supposed to be x as long as our x is in between -1 and 1 inclusive. This -1 is in that domain, so I can conclude that this just equals -1. The cosine and the cosine inverse undo each other. Part B, cosine inverse of cosine of 4pi/3. Well, your instinct might be to just say this is 4pi/3. However, 4pi/3 is not in the restricted domain of cosine that we're using when defining our trig function, our inverse trig function. So let's take a look here. 4pi/3 is approximately over here. The cosine of this value is an x value, and we have an equal x value for this angle up here. So instead of doing 4pi/3, I can also use just 2pi/3, and I'll have the same cosine value for both of those. So this is the same thing as cosine inverse of cosine of 2pi/3, changing it so that it's an appropriate input to use this inverse trig function relationship, and then I get 2pi/3 as the result. Now, what happens though if we try to compose a trig function and an inverse trig function, but it's not the inverse trig function of that particular trig function? And I know that just sounded crazy, but what I mean is, how do we calculate something like sine of tangent inverse of 12/5. I can't use that inverse relationship because sine and tangent inverse are not inverse functions of each other. But one thing I do know is since 12/5 is positive, I know that my theta is going to be between 0 and pi/2. Because that is where my tangent is going to be positive. So I'm somewhere in this quadrant over here. I'm just going to say this is theta. And let me make a right triangle. If that's theta, I know theta is supposed to be equal to tangent inverse of 12/5. Tangent is the opposite over the adjacent. So opposite would be 12, adjacent is going to be 5, and we can figure out the hypotenuse as well. Using the Pythagorean theorem, 5 squared plus 12 squared is this hypotenuse squared. So 25 plus 144 is c squared, 169 is c squared, and c is going to be 13. So let me fill in that hypotenuse, 13. So if theta is this tangent inverse of 12/5, then sine of that theta I can get using my triangle. Sine is the opposite over the hypotenuse, and I get 12/13. And that's all there is to it. So a lot of times we're going to have to draw a lot of right triangles to figure out some of these, but it's not too terrible having to do that. Let's do another one like this. Let's evaluate cosine of sine inverse of -2/11. So first thing I'm going to notice is if I let theta equal sine inverse of -2/11, the fact that -2/11 is negative implies that theta is between -pi/2 and 0. Because remember, for sine inverse, I'm going to get a value between -pi/2 and pi/2. But my sine is only negative in between -pi/2 and 0. So that we're talking about this region down here. So let me draw a triangle somewhere in this fourth quadrant. So I'm going to have, if this is my theta, some negative value theta, the opposite would be -2, but I'm just going to label it as 2. It's negative because it's going down. Hypotenuse is 11, and we can find this other value, I'll just call it A, up there. A squared plus 2 squared is 11 squared. A squared plus 4 is 121. A squared is 117. So A is the square root of 117. So here's square root 117. So then what is cosine of this sine inverse of -2/11? Well, it's going to be cosine of theta, which using my triangle, I have the adjacent, square root of 117, over the hypotenuse, which is 11, and cosine is positive in this fourth quadrant, so I keep it as positive, square root of 117/11. So to figure out if it's going to be positive or negative, you might just have to remember cosine is your x value, sine is your y value, and so anything in this quadrant over here has a positive x value, so the cosine is going to be positive. Let's do another strange example. Let's write tangent of sine inverse of x over the square root of x squared plus 9 as an algebraic expression for x greater than 0. Well, the first thing I would do is say that my angle theta is equal to sine inverse of x over the square root of x squared plus 9. And that means that sine of theta is x over square root of x squared plus 9. Now I can set up a nice triangle and use our right triangle trigonometry. If this is theta, sine of theta is opposite over hypotenuse. So the opposite is going to be x. My hypotenuse is x squared plus 9. And I don't know what this guy is. I'll just call that side A. Using my Pythagorean theorem, my a squared plus x squared is equal to my square root of x squared plus 9 squared. So a squared plus x squared is x squared plus 9. That means a squared is 9, so a is 3. So now that I know that this bottom side is 3, I can now calculate tangent of that angle. So tangent of that angle is the opposite over the adjacent, so I just get x over 3. And this was I don't even really need to write the tangent theta part. The x over 3 is that algebraic expression. That whole complicated tangent of sine inverse of x over square root of x squared plus 9 is a super fancy way of writing x over 3. All right, and to just finish up this video about inverse trig functions, we're just going to briefly talk about the other inverse trig functions for secant, cosecant, and cotangent. We don't use them as often, which is why they haven't been talked about yet, but they do come up sometimes. I'm going to make another chart. And we're going to start with the restricted function y equals secant of x. And the restriction's a little strange. We have 0 less than or equal to x less than pi over 2, or pi over 2 is less than x is less than or equal to pi. And we have absolute value of y is greater than or equal to 1. So that is where we're restricting our secant function. X can be any value between 0 and pi, except for pi over 2 because we have an asymptote at pi over 2. And the output is anything greater than or equal to 1 in absolute value. Then my inverse secant is defined as y equals inverse secant of x if and only if secant of y equals x, where the absolute value of x is greater than or equal to 1, and our y is between 0 and pi, but not equal to pi over 2. So again, the domain and the range flip. It's a pretty strange looking graph. Here's pi, pi over 2, 1, -1. At -1, I have a point up here at pi, and I just flatten out to a horizontal asymptote. And down here at 1, I have a point at 0, and I go up to that horizontal asymptote. And that's my inverse secant graph. It's very similar for cosecant. Y is equal to cosecant of x. My restriction is going to be x is between -pi/2 and pi/2, but not equal to 0. And absolute value of y is bigger than or equal to 1. Then my inverse cosecant is defined as y equals cosecant inverse of x if and only if cosecant of y equals x, and our domain and range flip. X is greater than or equal to 1 in absolute value, and my y, the outputs, are between -pi/2 and pi/2, but not equal to 0. In this graph, there's 1 and -1, pi/2, -pi/2. We have a point at -1, -pi/2, that goes up, flattens out to the x-axis, and a point at 1 pi/2 goes down and flattens to the x-axis, and that's a very rough inverse cosecant graph. And now we just need to define our inverse cotangent, and then we'll just do one brief example to finish the video up. So, if y is the cotangent function, we're going to restrict it so that our x is between 0 and pi. Our output is any real number. Then, y equals inverse cotangent of x if and only if cotangent of y equals x. X can be any real number, and our y is smushed between 0 and pi. So this is pi. Here's pi/2. I have a point at 0 pi/2. And the graph looks something like that. It has a horizontal asymptote of pi up on the left side, and then it flattens to the x-axis as it goes to the right. So last example, using inverse secants and inverse cosecants. We're going to evaluate in radians to 4 decimal places, which means you're going to need your calculator and you need it set in radian mode. Our first one, secant inverse of -4. Now, what this means is secant inverse of -4 is equal to theta. That's the same exact thing as secant of theta equals -4. And we know that our theta has to be between 0 and pi, but not equal to pi/2. Now, if secant of theta is -4, well, secant is the same thing as 1 over cosine. So 1 over cosine of theta is -4. And so that means that -1/4 is equal to cosine of theta. And now I have something I can use my calculator for. Notice we don't have an inverse secant button on a calculator, at least not most calculators. But I do have an inverse cosine button. So from here, cosine of theta is -1/4. So let me take cosine inverse of -1/4 is equal to theta. And if I type that into my calculator, I get theta is 1.8235 to 4 decimal places. Let's do another one. So when you're working with the cosecants, cotangents, and things like that, you really have to rewrite them in terms of sine, cosine, or tangent, because those are the ones we have buttons for on the calculator. Cotangent inverse -5/12. Well, this means if theta is equal to this cotangent inverse of -5/12, that means that cotangent of theta is -5/12. And we have theta is between 0 and pi. Now take a second and look at what that looks like. If I'm between 0 and pi, we're talking about this region up here. But my cotangent being negative means it can't be in this first quadrant because sine and cosine are both positive over there. So this tells me I have to be in quadrant 2 for this particular angle. So since I'm in quadrant 2, let me just draw a triangle over in quadrant 2. Then I can do cotangent is going to be adjacent over the opposite. And tangent is opposite over adjacent. Either way, I have 5 down here, the adjacent, 12 over here is the opposite. You can think of this 5 as -5. That's where that negative comes in. If I do the Pythagorean theorem, I get that this hypotenuse is 13 again. We don't have to do that if we don't want to. So this is what I got right now. I want cotangent inverse of -5/12, and I want to evaluate it in a way that I can type into my calculator. Well, cotangent inverse -5/12 gave me cotangent of theta equals -5/12. But that means that tangent of theta is -12/5. And if I happen to type that into my calculator, theta is tangent inverse -12/5, you're going to get theta is about -1.1760. But that's not in quadrant 2. That's down here in quadrant 4. How do I get it to quadrant 2? Well, if we add pi to it, it will flip it over to quadrant 2. So add pi to get the correct result, and we get pi plus our -1.1760 is equal to about 1.9656 radians. And that will put me back up here in quadrant 2 where I need to be. All right, so those ones are a little complicated because we don't have an inverse cotangent button and things. You want to rewrite it so you can use inverse tangent, and then you just might have to manipulate it a bit to get a proper result for the output of an inverse cotangent. In this case, we just had to add pi. That's usually all you have to do. If you have any questions on these inverse trig functions, feel free to drop them below. If you're a current student, you can also ask in office hours, email, or in class. And I'll see you guys next time.